Good morning and welcome to today's session on geodetic data analysis, where we will deeply examine what truly defines the quality of an observation in surveying engineering. When we step into the field with a total station, a digital level or a GNSS receiver, we are not just collecting raw numbers, but rather gathering physical data that inherently contains imperfections. In the realm of geodesy, the quality of these observations is not an arbitrary judgment of how carefully a surveyor stood over a tripod, but rather a rigorous statistical evaluation of the measurement's reliability, consistency, and closeness to physical reality. To truly master data processing and network adjustment, we must first break down the mathematical and physical pillars that govern the integrity of our field data. This brings us directly to our first core concept, which is the inescapable relationship between random errors and the overall quality of our survey data. Random errors, often referred to as accidental errors, are the small, unpredictable fluctuations that remain in our measurements, even after we have perfectly calibrated our instruments and corrected for environmental conditions. They are caused by unavoidable physical phenomena, such as microscopic variations in atmospheric refraction, slight trembling of the ground, or human limitations in perfectly bisecting a target. In geodetic science, we accept that random errors are a certainty, and we evaluate the quality of our work by how tightly grouped these unavoidable errors are around a central value. Mathematically, these random errors follow a normal Gaussian distribution, which serves as the foundational framework for assessing our data. When we say an observation is of high quality, we are statistically stating that the spread of these random errors is exceptionally narrow, resulting in a very small standard deviation. To isolate and analyze these errors, geodetic surveys rely heavily on redundancy, meaning we always collect more measurements than the minimum required to fix a position. By running these redundant observations through a least squares adjustment, we compute residuals, which are the differences between our actual field measurements and the mathematically optimized final values. The smaller these residuals are across our network, the higher the verified quality of our raw observations. As we analyze these distributions of random errors, here we naturally encounter two terms that are frequently used grossly error in everyday language but carry strictly distinct definitions in surveying, namely precision and accuracy. Precision represents the degree of refinement, consistency, and repeatability achieved within a specific group of measurements. It isolates the behavior of random errors and tells us how close our observations are to one another, completely independent of whether they are close to the actual truth. For example, if surveyor measures a baseline E 5 times using a total arc station and achieves readings that vary by only 1 millimeter AE, the dataset is exceptionally precise because the internal consistency is nearly perfect. Accuracy, on the other hand, shifts our focus away from internal consistency and directs it toward absolute truth. Accuracy is defined as the degree of closeness of an observed or computed value to its true, universally accepted geodetic value. Returning to our baseline example, if that highly precise group of measurements consistently yields a distance that is actually 2 centimeters longer than the federally certified national calibration baseline, the data is fundamentally inaccurate. This critical gap between a tight clustering of points and the actual true position is almost always driven by an underlying systematic bias, reminding us that high precision alone does not guarantee a correct survey. To bridge this gap between precision and accuracy, a high-quality observation campaign must actively identify and eliminate both blunders and systematic errors before any final data analysis begins. Blunders are gross error, such as misreading a height of instrument, transposing digits in a field book, or setting up over the wrong control point. And a single blunder can utterly destroy the validity of an entire network. Systematic errors are more insidious because they follow predictable physical or mathematical laws, such as the thermal expansion of a steel tape or the uncorrected curvatures of the Earth over long leveling runs. While blunders must be detected and entirely purged from our data, Systematic errors must be modeled and mathematically removed, ensuring that our highly precise measurements can finally become highly accurate positions. Once we have mitigated these errors, we must evaluate how different observations of varying qualities interact with one another, AU, which leads us to the concept of assigning weights to our data. In any complex geodetic network adjustment, it is rare that every single measurement is captured under identical conditions or with the same grade of instrumentation. To account for this, we calculate the mathematical weight of an A observation as being inversely R, proportional to its variance, meaning that measurements with lower random error are given a much greater influence in our final coordinate calculations. By applying this weighting system, a baseline derived from a high-end dual-frequency GNSS receiver surveying for hours will correctly dominate over a rapid observation taken with a false single-frequency receiver. Through the systematic management of random errors, precision, accuracy, and weights, we can confidently guarantee the rigorous quality of our geodetic frameworks.